So if it is true that Nas album done, and grammatical whatever aside, that's cool. I like Nas's music. I like that album with where he samples Inagata DeVita. No, the other one. Yeah. So, yeah, it's cool that Nas has an album done, but can I hear a song from the album? I mean, I guess it is kind of a cool idea that you put a song out saying, hey, I got a album that's finished. I'm assuming that song's not going to be the album, because having a song on your album saying my album's done is kind of redundant. But still, that's kind of a cool idea, but do you have to put the song on this guy's album and let him make the video and have the first 4 minutes just be stuff like this?
The keys.
I mean, J.J. Abrams last summer, I guess he could have made a movie or a short film called Star Wars Movie Finished. But he sure as shit wouldn't have put it on in a movie made by the guy who did The Room. And
Oh, hi, Mark.
hi. And it wouldn't have just been, Room jokes, Daisy Ridley and John Boyega passing a football back and forth on a badly CG'd rooftop. I don't know. Maybe I'm just getting old. I know I'm getting old, but still, seems weird. Anyway, I'll see you guys next time. No, wait. Gas stoichiometry. Yeah, we got to talk about that. So let's do a couple of gas stoichiometry problems, which by this point, you've had a lot of stoichiometry, and you probably got at least one more coming up in the next chapter. But essentially, it's the same old stoichiometry that you've done before, but now we've added some of that gas law stuff that you've probably talked about in this chapter. So, for example, let's look at this reaction between copper and nitric acid. And one of the products is nitrogen dioxide. And let's say you have 100 grams of it. And if all of it reacts, how much, or you collect the NO2 in a 15-liter flask at 298 Kelvin. Let's find the pressure exerted by the gas in that flask. That rhymed. So it's essentially a stoichiometry problem. It reads like one. You have 100 grams of copper, and you want to convert that to pressure. I didn't say the unit, but we'll use atmosphere of NO2. So yeah, stoichiometry. Convert this amount of this stuff to this amount of this other stuff. And the first step of any stoichiometry problem is to take what's given and convert it to moles. So we can do that here. We have 100 grams of copper. And if you're in General 1, you've been doing gram to mole conversions to death by now. Again, grams to moles use molar mass. So copper is 63.55. And the next step, as usual, is to convert moles of what you start with to moles of what you want to end with. And again, that mole to mole conversion, you just look at the equation. For every 1 copper, we're going to get 2 NO2s. Copper. So as far as where to go from here, we're looking for atmospheres of NO2, and there's no mole to atmosphere conversion factor. But I mentioned this, I think I did in another video. I can't keep up what order I do it in these days. I'm kind of all over the place, whatever I feel like doing. But in a question, especially at this point in your chemical education, if we're talking about a gas and we're talking about pressure and Cortana just popped up. Pressure and temperature and Kelvin, all of that just screams PV nRT. So, I mean, if you look, we're looking for a pressure, we're given a volume, we know what the gas constant is, and we're given a temperature. All we need to find the pressure of that gas is to know the moles. And if we stop here, that will give us 3.15 moles of NO2. And so we just plug that in with everything else and solve for pressure. So you can see it's a little bit of stoichiometry, a little bit of gas law stuff. I mean, I guess it's all stoichiometry, but you know, we're working the gas law in there. So we have 3.15 moles. And our gas constant, 0.08206 mole Kelvin. I know it can be a pain sometimes, but remember, whether you're doing unit conversions, I say this a lot in class, crooked, you still take the time to write the units to make sure everything drops out. Most of the time when I see people lose points on a test, it's because I see a bunch of numbers with no units and they make a little dumb mistake. So yeah, the only unit left is atmospheres, and we're trying to calculate atmospheres. So you plug that in and you get 5.1 atmospheres. Now let's look at another example. Now we'll look at the reaction between sodium sulfide and hydrochloric acid, and you get sodium chloride and hydrogen sulfide. So now we want to see how many milliliters of 2 molar sodium sulfide we need to make 5 liters of hydrogen sulfide at this pressure and temperature. What some might recognize as being STP, but it's okay. But again, same setup as every stoichiometry problem. Convert this much of this stuff to this much of this other stuff. Here we're starting with, you know, basically 5 liters of H2S at that pressure and temperature, and we need to convert that to milliliters of sodium sulfide. So yeah, first step of any stoichiometry problem, take what's given and convert it to moles. I say that so much during this part of the semester. It can be maddening, but compounded over 15 plus years. But you know, before we take a volume, we could use molarity to convert to moles, but we're not given the molarity of H2S, but we are given pressure and temperature. And again, whenever you see pressure, especially at this early on in chemistry, you're probably going to need PV and RT. So let's see, we are given a pressure, we're given a temperature, we're given the volume, we know the gas constant. We have everything we need to convert that volume to moles. So let's do that. So you plug that in, and was that PV over RT? Yeah, I didn't give myself enough room, so I'll just go ahead and work it out. It is there it is, 0.223 moles. That is where it is, yeah. Right. So now we're in moles of what we started with. From here, it's just like any other stoichiometry problem. To go from moles of what you started with to moles of what you want. You look at the equation. If every 1 hydrogen sulfide, you're going to need 1 sodium sulfide. And since we know the molarity of sodium sulfide, we can use it to go from moles to liters, like you probably did a lot in the previous chapter. So it's 1 liter is 2 moles. And that will give you 0.112 liters of sodium sulfide, which converts to 112 milliliters. So, again, as far as how the question is set up, again, it's set up, both of them are set up like any stoichiometry problem, but when you start to see stuff about a gas, and especially if you see pressure and temperature, all that jazz thrown into the question, you're going to need the gas law in there. Either at the end of your stoichiometry problem, like we saw in the first example, or in the last example, we started with the ideal gas law to get into moles of what we wanted. So, yeah, it's kind of a bit of a mix of a few things that you've talked about before, but it's nothing really new. It's just some stuff put together in sort of a newish way. But that's it for now. I will talk to you guys later. Bye.